Okay, this actually carries us through the N4, N5, and questions. The P1 question asks, well, if we operate between 300 and 370 Kelvin, which is the temperatures we had just a minute ago, but this time only raise the water 0.9 meters before allowing the gas to expand and expel water. Still raising the final temperature to 370 Kelvin, which will expel more water than if we'd raised the water in the tube to 1 meter. We want to compare the amount of work that we can get out of the system and also the energy we have to put into the system. We're going to have to put more energy into the system here because more of the temperature raise will occur at the constant pressure because we get to the 0.9 meter height more quickly. We have more room to expand. We'll get to this more quickly at a lower temperature, leaving us more of a temperature change through which to expand the gas at constant pressure. So we're going to have more water raised to a lesser height. More water raised because we'll have more expansion. Lesser height because, of course, 0.9 meters is less than 1 meter. We're going to have less temperature change at constant volume, more temperature change at constant pressure. Since it takes more energy to expand the air, did I say water? But in any case, since it takes more temperature change to expand the air at constant pressure than at constant temperature, it's going to require more thermal energy, more delta Q. So, do we get more or less potential energy change? Do we get more or less, do we require more or less heat energy to accomplish that change? Okay? So from state 1 to state 2, the calculations here are practically the same, and without the precision that I was using before. In state 1, the pressure needs to be about 109 kilopascals, and that's going to allow us to expand the gas a little bit more. Well, pressure is going to be 109 kilopascals, temperature is only going to be 327 Kelvin, and the volume is going to still be 0.5 liters. Okay, the 327 Kelvin now can change by from 327 to 370. The volume is going to be 327 of the original volume instead of 373 thirtieths. So there's going to be more of a volume change, and I'm going to say maybe that's 0.57 liters. Now, I haven't worked these numbers out carefully. I really don't know whether this is going to be, for the 0.9 meters is going to give us more or less change of potential energy. And I don't know if it does give us more, if that's going to be enough to compensate for the additional delta Q. So I'm just outlining the problem here. Again, from state 1 to state 2, pressure has to go to 109 kilopascals, and the temperature will go to 327 Kelvin. And then from state 1 to state 2, the volume is going to go up to maybe 0.57 liters. It's going to be a little more than it was before. Don't know if it'll go all the way past 0.565 to round off to 0.57. And we're not using enough significant figures here to really understand these, or to really quantify these differences enough to make good comparisons. You can do these calculations to more precision and determine that for yourself. So, what's the delta Q from 0 to 1? What's the delta Q from 1 to 2? Well, from 0 to 1, you only have a 27 degree change, 27 Kelvin. You still have the 0.02 moles, and you still have the 5/2 R. Then you're going to, from 1 to 2, you're going to do this with the 7/2 R because you're expanding, have to do the work of the expansion. And you're going to have more of a temperature change. Instead of a 40 degree temperature change, you're going to have a 43 Kelvin temperature change. Now everything here follows from very approximate calculations, and the difference in efficiency, the differences in work are small, so we really do need more precision, but I'm going to kind of leave that to you, and actually I'm going to encourage you, I'm going to ask you in analyzing the lab to do all this symbolically, do the calculus to optimize the efficiency. So I'm not going to worry too much about little differences here. I'll just point them out. Okay, so the delta Q from 0 to 1, you got a 27 Kelvin. Maybe that's 11.5 joules, somewhat less than it was before between state 0 and 1 when we raised the water a little higher. From state not 0 to 2, but state 1 to 2, the delta Q is going to involve the 30 joules per mole Kelvin, the 7/2 are, and a 43 Kelvin change with 0.02 moles. Maybe that's about 0.26 joules. So is that more or less than what we had before? Well, it's 37.5 joules. Before it was 36 point something, so it is a few more joules. We don't know accurately enough just how many extra joules we get. But if we do the calculation precisely, which we certainly can do, we can determine that. The change in potential energy. Okay, well, remember I estimated that we go up to 0.57 liters. Now that 0.57 is only enough to say that we have a 70-gram mass. We don't have enough significant figures to make the 0 significant. So only the 7 is significant here. We only have one significant figure in the mass of the water that's expelled here. It could be 64, 66. Don't think it's as much as 70. And anyhow, whatever, if we get this number and we do the calculation precisely enough, we can get a more precise number here. Multiply that by the height and by the acceleration of gravity, and we get something that I estimate to be 0.63 joules. But I've made the note here, this one significant figure here is unreliable, and we can't conclude a second significant figure here. So this is just a pretend quantity. I doubt that that's going to be accurate. Using these quantities regardless, we're going to pretend this is accurate. So the efficiency at the 1 meter height, you remember, was 0.6 joules over about 36 joules. The potential energy change we got out of the system divided by the energy we had to put into the system, and that's 0.017. Here, if the 0.63 joules is right and the 37.5 joules is right, we get something maybe closer to 1.06. It's going to be less than 0.017. I don't know if it'll go all the way down to 0.016. So these figures would imply that there's less efficiency at the 0.9 meter height than at the 1 meter height. But again, we can't really take that to the bank. We'll have to work out the figures a lot more accurately to draw any real conclusion here. The difference will be slight, so we're going to need more accuracy in the figures.